Okay, sorry for the delay. So we're going to try to submit the simulation basically right now, and then we'll try to understand what we just did while it's running. The simulation should take about 10 minutes, and by the time we're done explaining to ourselves what we just did, we can look at the results of it. And then I'll talk for just a minute or two about how you could do this yourself without me just sort of feeding you the scripts to run it. Okay, so in the terminal that you opened up, you want to type in this command. We're going to clone a Git repository that contains all the setup files for this simulation. There's an S on it. It's HTTPS, and then it's me Donovan R / weighted ensemble. Oh no, that's absolutely the wrong link. I'm sorry. Don't do that one. We want this one. It's a WEMSL example cube frank.git. If it goes correctly, it should say it downloaded some stuff. And then you just want to cd to that directory that you just downloaded. WEMSL example cube frank. And then ls should list these files there. And that's sort of a standard array of configuration scripts that you need to start a WESTPA simulation. My directory looks a little different because I already ran the simulation. Okay, so after you clone the repository and change into the new directory, we submit the job with one command. It's qsub, and then submit job.pbs, and then hit enter. That should submit it. And
You gotta submit.
Albert. Okay, so we submitted a job. So what did we just do? We submitted an MCell job. MCell, as Dan talked about, is a simulation framework for stochastic reaction diffusion simulations. And so I think he also made the point that these cellular systems are complicated enough that they face the same sampling problems as the MD world or structural simulations in general do. You can approach these problems with a couple different frameworks. One is to not even care about geometry and just keep track of the amounts of molecules that are in a certain volume. That's sort of a non-spatial approach, and we worked on that a few years ago. That works sometimes when you don't care about the geometry of your system. Sometimes geometries can be quite complicated and important. This is a dendritic section with some spines on it, and it turns out that geometry is very important here. And so in general, thinking about geometry is something you should do when you're doing these simulations. And MCell is a simulation framework that is able to do this. And so this is what we've been working with. in simulations that are not quite as ambitious as this, but sort of similar. And so it's really nice that WESTPA's dynamics interface is so modular, because we were able to use basically the same setup as you would for a structural simulation to do these kinds of simulations. And that's what we just submitted. And so we came up with a whole pipeline to make these models. There's a lot of this software is developed by our collaborators in Pittsburgh. But essentially what we're doing is using WESTPA to manage a bunch of M-cell trajectories in this sort of tree that Matt showed you. You can create these things in a visual editor and whatnot. The system that we are trying to publish a paper on is sort of this realistic cellular system. It's quite large and complicated, and this turned out to be a really nice approach for systems like this, where you sort of, you come up with a geometry from maybe imaging, and then a reaction network, and then sort of glue the two together in a spatial simulation to see how much spatial effects matter. And it lets you measure, the same sort of rare observables that we've been talking about. Looking at the probability distribution that you have a certain number of protein molecules in existence. So you might have this signal cascade where all these reactions follow one another, and you want to look at the likelihood of something far downstream. Can be a very rare event, very difficult to sample, and the same techniques work here also. And also these sort of maybe slightly more involved measurements of first passage times. Also, the same machinery works here. And so these simulations would take about a day to do 100 seconds of dynamics. So it's so much faster than a structural simulation, but it's also slow on the timescales that you care about. The simulation that we just submitted should take about 10 minutes to run, and so the dynamics are trivial, essentially. And it's actually one of the situations where the weighted ensemble resampling is significant compared to the dynamics that you're running. It's actually the file reading and writing that takes up the most of the time we're waiting. The simulation would run in maybe 10 or 15 seconds if we didn't have to read and write files. So that might be something to think about, making a better interface for not having to do that in the future. So this is the toy model we just submitted. And what happens is you have this cubical volume, and these ligands start bound at the top, and then they can diffuse and bind to the bottom, and they bind with equal probability to the top and bottom. They just start at the top. And so we wait for a little bit, and we want to see how many are bound at the bottom after, I think I set it up so that we run 1,000 iterations of weighted ensemble resampling, and at the end of that we see the probability distribution of things being bound at the bottom of this sort of cubical cell thing. So the way that an M-cell simulation works is that it's described by these model files. So we can take a look at them. They're very, very simple. We didn't do anything really magical. So let's move back to the terminal, and in the main Git repository, just sort of take a look at those files real quick. So we can just spit them all out with cat. They're in the basis states directory, B states, and there should only be one subdirectory there. It's example system cube, and let's see, what should we look at first? So there's a geometry, and then you define some different molecules to live there, and you define some reactions to take place. So we can look at the geometry, and it's just a cube. You make a list of vertices and how to connect them. It's a 20, 30 line file. The molecules that live there one of them has a diffusion constant. The surface, that's the one that can diffuse. The ones that live on the surface don't move, and that's all it takes to describe that. And the reactions between them are just described by this simple reversible binding. So the volume molecule binds to the surface molecule, becomes a bound form, and then it can unbind also. And it's the exact same thing at the top surface and the bottom surface. So let's see, and then I guess it's also worth looking at the runseg.sh files. And Matt mentioned that you write this shell script that actually sort of does all the work for you of starting trajectories, reading the progress coordinates. So maybe vi the runseg file, and we can sort of look through it. And so this is pretty generic. So this is for an MCell system, but it looks pretty similar to what it would be for like a structural simulation. Also, so you find where you are, and then and where you want to go. You define. I define, the program that we're going to run, this MCell variable. So in theory, you could use different versions of it or whatever. And there's only a couple of things that you actually care about, is like the name of the folder that was sitting in the basis states directory, and then the name of the molecule that you care about. It's this bound state of a molecule, and that's just the syntax for how much exists in the whole world that MCell is simulating. So that's your observable one, is the progress coordinate for weighted ensemble. And then so yeah, you basically just run dynamics. So if you're at the first iteration, you just run dynamics. If you're at later than the first iteration, you have to restart. So there's a little bit of syntax for that. It's not really important. And then you read your data files. So I'm writing out data about the reactions that are going on. You just sort of read through them and then pipe them into these progress coordinate returns, and then WESTPA will read those. And WESTPA also has the capacity to you store your progress coordinate. That's really important for weighted ensemble. You also store arbitrary auxiliary information, and so I just have it pasting in everything we write out in this directory and storing it. And so that's what 60 lines of a bash script to that runs the dynamics for every single one of these trajectory segments through the 1,000 iterations. That's pretty much it for what makes up the simulation. So it might be worth checking how we're doing again. See if we're done. I'm still running. It's been 12 minutes. Has anyone managed to finish a simulation? David finished?
I'm on 78 out of 100 iterations.
Okay, so it's only for 100.
Where's the status?
Yeah.
West log?
Yeah, you might not be able to actually get the status.
Yeah, you have to log into the nodes.
Yeah.
What about West log?
If it's in your directory,
Because the whole thing, you copy the whole thing onto the node.
Yeah, so
Iterations.
It's not updated.
Yeah, so
Right.
basically,
Yeah, but mine's finished.
Okay. Oh, is it?
Copy back.
Oh, okay.
yeah,
Then yeah, if it's finished, you can check it.
it's running on a node, and it'll copy back to the folder when it's done.
So all the SH scripts are what the user has to write or optionally writes?
More or less. So when I mess with this stuff, I mess with the runseg.sh file is how each trajectory segment gets propagated, and so that's a really important one. And then maybe we can look at these real quick. There's a configuration file. No.
But like there's that environment.sh, which is kind of important.
Yeah, so most of these ship with the various examples that come with WESTPA.
But that's
the
sort
structure
of
that we found
implicit
convenient.
known if you see end.sh, it does that. Like what is W init? What is W run?
So those are the actual commands that
Right.
WESTPA uses. So now these are all the shell scripts that have been written to automate that. The really critical one is runseg.sh. So that is what does your dynamics. And so all the other stuff is kind of window dressing for making this a little bit easier in practice. But the thing that the user, absolutely has to write is runseg.sh or its equivalent.
Well, you need to report the coordinate direction.
That happens inside of runseg.sh.
Yeah, because you can just manually
Yeah.
the simulation.
Yeah, so that's the main one, and
Oh, P chord 1.
yeah, that's the, or something like that. I usually wind up messing with system.py that defines the bins, and then the west.cfg is the configuration file. Oops.
And if there's 2 coordinates,
There's 2 coordinates, then so then the system.py file is where you define the bins, and so here the bin bounds are defined basically from 0 to 1,000 in steps of 1, and then some padding on the sides. This is where you could get crazy if you wanted to, or you can do these sort of nesting bins, or the 2D is as sort of fancy as I've gotten, and you more or less take a Cartesian product and export it. Matt could probably explain that a
Yeah,
bit
so
better.
that very first line up there under initialize, that the self.pcord endem, that's how many dimensions your progress coordinate is. So if you had a 2-dimensional progress coordinate, you would set that for 2. And then where you assign bin boundaries, instead of, so that is just Python syntax for give me negative infinity, 0, a half, 1, 1.5, 2, 2.5.
yeah, but so that's a global variable, right?
And then that gets put into that, it's bin mapper there. All right, there's only one instance there. So there's
global variables, sorry.
yeah, so we're saying construct a bin mapper that's on a rectilinear grid.
Oh, okay, so what really matters is this bin mapper.
Yep, that's
That
what
will
really
take
matters.
the coordinate to the bin. So you have a class for the Voronoi.
Yep,
Okay.
yep, and that's.
And what if I wanted to do WE explore, we explore, how do you pronounce it?
W Explorer.
W explore.
We're not shipping that plugin yet because it's
still
experimental,
work
but
in
we can talk
progress.
about it. We can talk about
Is it in Git?
it somewhere. Yeah.
So
Is
that's
it
Probably
in
in
Josh's
Josh's.
Josh's?
order.
Yeah,
Yeah.
yeah, it's probably in Josh's GitHub.
And it still needs to be tested.
Yeah.
So yeah, so there's that's one of the main files I mess around with, and it's interesting that you asked that because after a while I got a little bit sick of hand tuning. So one of the amazing things about Mat software is how flexible it is, but I really just wanted to do very simple things with it, and so there's a couple of places where you have to change the same variable twice, which makes a little bit of sense because you're getting 2 different pieces of software to talk to each other, and so I have to tell my dynamics engine that I want to propagate 100 time points per iteration, and I also have to tell weighted ensemble that it should be expecting 100 time points per iteration to read them in. But it got a little tedious to do that every time I wanted to change something, so I wound up making this tool that's just a shell, like a Python script to take in a folder that's just a model, so an NEM cell model, and give it a couple really basic configuration variables, and these are all the things that you need to set in weighted ensemble, maybe in the system.py file or the configuration file or the runseg file, but they're all just right here, and so you just fill out this list and it does it for you. And to make it easier for people to use, I made a website so you don't even have to download anything. You just upload a zipped file of this model that you care about, and you fill out a couple things that you need to know for weighted ensemble, right? You need to know what your progress coordinate is. You need to know how many iterations you want to run, whatever, it can be anything you want. How many steps in your dynamics engine, so like this would be the same as setting like how many picoseconds are in your weighted ensemble iteration, how long that is. So how many time steps do I want to run? How often do I log data? And then you fill out, what are my bins like? How big do I want them to be? How many trajectories per bin? And then, like where's my Python? Where's my weighted ensemble? And let's see if this works. No.
This is just a wrapper to run it locally on your own machine.
So this is just a wrapper to fill out all to take a model in whatever you like to use and to spit out a weighted ensemble simulation of it, and then you can run that weighted ensemble simulation wherever you want. So this is just going to download it.
So the zip file that you gave me didn't have it in there? Yeah, this is Rory.
Just going to save this guy. So it spits out basically the ready-to-run weighted ensemble, which is exactly more or less what you downloaded from Git. It's just, you can, it's modular, you can change whatever you want, do whatever you want to it. Yeah, Nick?
So that's just works with MCell?
Yeah.
Okay.
Yeah. It took me a week to make this. It wouldn't be hard to make it for something else. Yeah. So let's see.
So, changing the bins at runtime, do you change the system file?
Yeah, you can actually change it at runtime. The simulation, you have to stop the simulation, then you change the bins in that system.py, and then you start it again, and the bins are new.
If I just kill the job, does it gracefully?
Usually. I told you that we're revamping the
forking.
Yeah, we're revamping the multi-core handler. It almost always exits gracefully. This is why we're still in beta though, because it doesn't happen 100% of the time, and it doesn't kill all your data. It doesn't exit gracefully.
Okay, so then when you start it again, it sees that these directories are populated, and
It knows to restart from the proper place.
At the worst, it's going to drop back to the beginning of the iteration that you're on and rerun. So if you're halfway through running an iteration of weighted ensemble, that half will be gone when you restart, but previous iterations will be there. That's the worst case, not the common case. The common case is it just knows where to pick up where it left off. And it's a little more subtle than what files are there, because those may or may not be in good shape if you kill it in the middle of a run. Only segments that are known to have completed successfully will not be run. Does that answer your question?
yeah, and that west.h5 is sort of the metadata.
Yeah, that's the master file. It's got
So if that gets corrupted, you're screwed.
pretty much. That does not. It happens often enough that you probably want to back that up every week or so, but
Yeah,
not
we
so
back
often.
it up periodically.
Yeah.
So maybe we should check and see if our job's finished again.
It's still running.
Yeah, mine is still.
Okay, well, it's been a while. Maybe we should think about moving on. So there is you should have cloned an example data file, and we can look at the example one, and then you can go look at the one that you submitted in a half an hour or however long it actually takes to finish. So if you ls that directory, you should see a west.h5 file, and that should be the example one that you downloaded, or if your simulation ran, it'll overwrite it with a new one. And so Dan talked about these different ensembles that you can look at, the equilibrium or steady state or initialized one. And what we're doing is just initializing from a delta function and looking at that spread. So this is not an equilibrium or steady state simulation. We're just looking at a probability distribution evolve in time. So let's do that. And so let's change into this ASCII plots directory. And you should be able to just / ASCII movie .sh. And it'll make a plot for you of, oh, it's cut off there, but it ticks through the different iterations. And you look at the probability distribution. So for a long time, this is iteration 30 now, before something happened. And you can watch the weighted ensemble histogram evolve. And also see this cutoff where, given an equivalent amount of brute force data, you couldn't see below this other line, right?
Can you explain that again?
So we're looking at a probability distribution evolve in time. This is on a log scale. So this is the probability on the y-axis, and the x-axis is the number of bound receptors at the bottom of the cube. So
what is time? There's a third implicit axis of time here.
as the movie progresses.
Yeah. What
So
is that?
So there's 100 weighted ensemble iterations that we ran, and so this is the snapshot of the probability distribution at each iteration, and then the next one, and then the next one, and then the next one.
Okay, so it's at the very top.
It's at the very top, and it updates.
Whose idea was it to do this in ASCII? Because that was brilliant.
That was me because I didn't trust the X score.
There's wisdom in that.
But I guess it was whoever developed GNU plot, because there's an ASCII output for it, which is cool. So yeah, anyway, you can watch this distribution evolve in time, and it's pretty clear that you can see much farther down into the tails of the distribution than a brute force approach would let you see, given the same amount of sampling power.
What are the A's and the pluses?
So the A's are the symbol for the PDF,
Okay.
and then the pluses I think are just tick marks for
Okay.
the axes, and then this is the cutoff. So yeah, unfortunately we couldn't look at the ensemble of different distributions that we would get. I guess you got to look at your own. No. Was it roughly the same thing? Different, but yeah.
It's a little noisier.
Okay. Yeah. So there's definitely some variation in what you see in each weighted ensemble run. That's sort of what we were talking about with running multiple independent weighted ensemble runs, and clearly there's no error bars or whatnot here. But this is an example of what I would use this for, to look at these distributions as they evolve. And so, yeah, like I mentioned, this is pretty easy to set up and do yourself. I made this website that lets you do it, that you can't access unless you're on the CompBio VPN. Eventually, it's going to be up for the public to use, and until then, if you really are enthusiastic, you can use the command line script to generate these models yourself if you want to. And there's instructions for how to run them on your laptop. It's basically the same as what we just did without the submission script. And they run actually faster on my laptop than they do on the cluster, because it's all file reading and writing, and the SSDs are way faster with that.
Can I extract a trajectory?
Matt,
What?
can he extract a trajectory?
Absolutely. Adam, are you going to talk about that?
I think Ali's going to talk
Ali's
about
gonna
that.
talk
about
It'll
that.
be-
We'll
it'll
get
be
to
the
that.
analysis tutorial.
Cool. Well, I think I should probably wrap up and let someone else take over.
Yeah, is that everything you wanted to cover?
Yeah, it's unfortunate that the simulations didn't finish, but same effect, you know.
Okay.